Hello everyone. Today we will be talking about Textron, which is a weak supervision based framework used to carry out text detection in documents. Before understanding Textron, we should understand why do we need to use it in first place. So, text detection has been taken care of in various kinds of algorithms, right from deep learning, machine learning, with dependency on lot of labeled data sets, as well as computer vision based algorithms. If you see, the DL based methods are really data dependent, so they don't do very well when they are seeing some new data or when there is limited label data for certain languages. On the other hand, CV based methods are less data dependent, but they are sensitive to noise. As you can see in this image, a single word can be engulfed or fragmented with more than one bounding boxes. Similarly, a DL based method can incorrectly engulf more than one words in a single bounding box. So these inconsistencies are taken care of by Textron, because in a weakly supervised manner it can try to combine the strengths of both the DL based methods as well as CV based algorithms and give us consistent word level bounding boxes in order to get seamless text detection. Over here you can see a sample for handwritten Devanagari text. And as to why Textron, because this gives more flexibility to users because they are aware of the strengths and weaknesses of different text detection methods and also are aware of the nature of the scripts of the text which they wish to detect. And of course you can combine to get the best of the both worlds, CV based approaches as well as the DL based approaches. Because we are dealing with languages which have less label data or they are low resource by default, we try to leverage the predictions of certain DL models that have been pre-trained on a significant amount of language data for some abundant language, and that we could use in conjunction with other methods to improve text detection in low resource languages. This also eliminates or reduces the dependency of label data. And there have been tons and tons of work for text detection overall. A lot of DL based text detection methods which explore the paradigm of object detection or segmentation. Then there have been early CV based text detection algorithms too that try to leverage the concept of edge detection or connected components and so on. And recently there has also been a rise in weak supervision for text detection, such as text as lines or vtext. But one such deep learning based method that has been seeking a lot of recent attention is the DBNet, or the differential binarization as it works on. It was used for real-time scene text detection, but they have also shown to be performing very well for document text detection. Hence, DBNet also forms one of our baseline in evaluating Textron. Since we are trying to exploit the paradigm of data programming, we need to understand the notion of labeling function. So, labeling functions are conventionally noisy functions which are responsible for creating weak labels. So the function, it takes an input as some document image or a document page, and the output will be a corresponding binary map where either text or non-text region is represented. They work on the pixel level, so a LF can either label a pixel as text or non-text, or it can abstain from labeling completely. Here are examples of few labeling functions. One thing to note at is a labeling function is trying to trigger or will fire for a certain pixel only for one class. So these labeling functions trigger at the black regions and they label text. So all the black regions, as you can see for the corresponding binary map, have been labeled text by these labeling functions. On the other hand, we also have complementary labeling functions. Here they also trigger the black region, but the difference is they label non-text regions. So they abstain from labeling the white region and they label the black region. We need complementary labeling function because one labeling function is associated with only one class, and we need to take into account both the classes text and non-text, hence we have another set of labeling functions. And it is the interplay of a lot of labeling functions which actually lead to an aggregation, or which actually lead to the usage of Textron in order to get a final prediction. So as you can see in our proposed methodology, an input page goes through two major stages. One is the LF application stage, where number of LFs have been applied on the same input page to get their corresponding binary maps. Before applying the LFs, they actually also undergo a shrinkage pre-processing step, about which we will be talking further. After the application stage is over, we next go on to the aggregation stage, where the first thing which comes into picture is Textron. That is, the usage of Textron model helps to aggregate these countless binary maps into a single binary map to get our binary prediction. These predictions are highlighted in Y as seen in the figure. Once we have the final binary map, then they undergo a label generation step in order to get the word level bounding boxes. The LF application stage has this pre-processing stage of shrinkage of the LF outputs. This is done in order to recover, or in order to maintain, the word level demarcation of the bounding boxes. As you can see in the image, if we do not apply shrinkage, the boxes can tend to overlap and the word level demarcation is lost. And this might not be easy to recover them in the label generation stage. Hence, in the application stage itself, as a pre-processing procedure, we perform shrinkage of the height and width of the bounding boxes, which label the corresponding text. Next, we move on to the label aggregation stage, where we come across Textron. Here, Textron is responsible for aggregating the votes, or the triggers of various LFs into a single assigned label. So in the training phase, each LF is actually consisting of two parameters, one for each class, and Textron tries to estimate the probabilities that a pixel belongs to a certain class or not. While in the inference phase, once Textron is saved with those parameters, it tries to compute the probabilities that a pixel belongs to a certain class based on the output of the LFs and the learned parameters. So we get a final assigned label for every pixel. And because every pixel can be assigned a text or a non-text label, the final output of Textron is also a binary map, as you can see in this image. This binary maps undergoes a contour-based post-processing, which is responsible for creating the word level bounding boxes. While regenerating the bounding boxes, it is taken care of that the shrinkage of the height and width is again enlarged to recover the original size. And these final bounding boxes are then plotted onto the input image, just as to see how our text detection performs. Because we are trying to perform text detection on a multilingual setup, we actually have a plethora of documents of English language as well as Indian languages and different modalities as well, printed and handwritten. We have a lot of training sets, validation sets, and corresponding test sets on which we report the performance of Textron. The training sets are usually used for training the Textron parameters, while the validation set is used to fine-tune the labeling function hyperparameters like the thickness of the contours or the shrinkage of the width and height, which have been applied for the pre-processing stage. And we use the test set to report the results on various languages and modalities. Our analysis and training includes performing unsupervised analysis of the LFs. Since we are dealing with lot of unlabeled document images, we try to understand the coverage, overlap, and conflicts of all the LFs and try to determine a combination of LFs which will be good to go to. And we have finalized a combination of 8 LFs, as you could see: DBNet, Tesseract, Contour Based, and the Canny filter, and their corresponding complementary LFs labeled as the reverse LFs. And we then use the training set of unlabeled images for tuning the parameters for Textron. The validation sets are used to fine tune the hyperparameters like the shrinkage, the width shrinkage, the contour thickness, the edge thickness, and so on. And we have determined few hyperparameters that have been optimal for certain kinds of languages and modalities. We use this on the unseen test sets to report the precision, recall, and F1 score of Textron. The inference is similar. Over here, the hyperparameters as well as the Textron LF parameters remain unchanged. The final output is a binary map which undergoes label generation step, and then the retrieved bounding boxes are compared against the ground truths, and we get the precision, recall, and F1 scores respectively. As you can see, this is the performance of Textron for TalkBank, which is for English printed modality on 100 test samples. Overall, Textron does perform better. There are certain classes where there is still a scope of improvement for Textron, but overall Textron on English printed modality has shown to perform better. On the other hand, if we look at the Indian language text detection test sets, Textron does perform better for printed Tamil and printed Gujarati dataset as well as handwritten Devanagari dataset. We also present the qualitative results below. As you can see, Textron tries to eliminate false positives or also tries to correct the missed detections. It also has shown to perform very well for Devanagari text, handwritten text detection with higher IOU thresholds as well. So all in all, Textron does help in multilingual text detection using a data programming based approach, and that could be used for different recognition stages or end-to-end OCR as well. We have also concluded that there is scope of improvement in detecting the graphical objects like table and equations, for which we will be trying to investigate or explore new LFs and perform layout analysis of the page. Further, Textron has also shown to perform very well for Indian printed as well as handwritten text, so this can also be used to expand the scope